Okay, so let me go straight to the main idea. So those are functions that undo the effect of is the function that undoes the effect of the original function. So that's the function that we have been dealing with for a while as an illustration of all kinds of mathematical things about functions. So this one, the arrows point from boy to the ball he plays with. So so boy, 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 boy. So boy plays with ball. Okay, so that is the question answered by this function. Okay, so now we could easily think of a question to be reversed. So ball, I'm writing from right to left, is played with by boy. Okay, it doesn't work out too well. But you can see I wanna go from right to left. So the ball is where we're starting. The starting point is the ball rather than the boy. So those arrows point from boys to the balls. From each boy there is an arrow pointing to the ball he plays with. Okay, now if I want to go backwards and ask, looking at the ball, I ask myself, who is the boy who plays with that ball? Okay, so which would simply based on the same data. So so then what's going to happen? I'm going to try to reverse the arrows, right? So I'll just go with this like this. So it's the same relation. The relation remains the same. So the relation is between boys and balls, and that doesn't change. But the function that function that we started with, let's say this one, f. Okay, from boys set x to set y of balls. Now I want to go backwards and ask myself, what is the opposite relation? So can I determine the boys that plays with the ball that is shown to me? Can I? You could try. You could try because there's enough information of it. But what about it is a question, okay? The problem with this question that it doesn't have a good answer. So this one is okay. This question has a good answer. We started with it, and those black arrows indicate the answers to this question from a boy to a ball. Now, if you want to go backwards, you see the problem that we are facing with the second question. What? That's right. So as you can see, basketball is played with by two boys. So then there isn't one single answer. So that's one problem that we point out. Do you see other problems?
Football.
What?
Football.
Football. Same problem with the football. Once again, so the problem is that two boys playing with it, and therefore there is no one single answer. Any other problems? Yeah. Nobody plays with baseball. Okay, so actually three problems of different nature. Can you classify these two problems in the light of our recent discussions? Two boys play with the same ball, basketball. What is it? You don't have to raise your hand, just
Not one-to-one.
So indeed, f is not one-to-one. So f, even though it was a function, the problem with it was that it lacks certain degree of regularity. It is not one-to-one. So there are two arrows converging on the same ball, actually twice. So once again here, that function f of ours we started with is not one-to-one. And then secondly, what's the second problem? Nobody plays with baseball. What does it tell you? F is not onto it. Okay, so these are two different kinds of problems, and they're classified. This problem and that problem are produce the same two different types of irregularity of functions, and as we can see, both of them create the same unsurmountable problem when we try to reverse our question. So when we're going backwards, either one of these two problems will create the same impossibility to have a function, because there will be two arrows originating from the same ball, which is not allowed for functions, or there is no arrow originating from baseball. That's another kind of problem. Okay, so both of them will entirely ruin our chances of having such a function that would give us the opposite or inverse relation between the two sets. Okay, so so this is what I'm talking about, is the relation. Is it? Yeah. So I put this picture here in order to emphasize the point that the relation is working. So there is nothing wrong with the relation between the set X of the boys and the set of Y of the balls. It's just as long as we do not choose which one is the input, which one is the output, we are okay. It is when we want to create a function going in a particular direction that's where we have all of these problems, and they're well, you just saw them right here. Okay, so let's see what would make this answer, this question to be answerable is when both of these two problems, 1 and 2, would have to be overcome, or rather we need a function f to begin with that is both 1-to-1 and onto. Okay, so that's pretty much the answer for this problem to exist. You'd need to not to exist. You'd need both of the problems to be prevented from happening, and that's how you had to know ahead of time that those problems do not exist if you declare the function or require the function from the beginning to be 1-to-1 and onto. Not every function is 1-to-1 and onto is this example. We have functions that are onto but not 1-to-1, or vice versa, but this one is really bad in two ways simultaneously. But when we do require the function to be 1-to-1 and onto, it is actually looks kind of a plane. This is an example of 1-to-1 onto function. I added an extra ball, and then as you can see, there is exactly one arrow starting arriving to every ball, and every ball has an arrow. Okay, so this one is 1-to-1 and onto. 1-to-1 and onto. So that is a very strong requirement, and as you can see, the result is kind of interesting, because we do not have. It is like they become replaceable. The correspondence becomes 1-to-1 onto, meaning that for each ball there is one boy, and for each boy there is one ball exactly. And so then you could for example. If you don't remember what that ball is, for example, you can say, instead of saying that's a basketball, you say, well, that's a ball Tom is playing with, and that would be totally unambiguous. And conversely, if you don't remember what that the name of Sid, then you say, well, it's the boy that plays with the soccer ball. Okay, and that will be still entirely unambiguous and fair. Why? Because this is what is called a 1-to-1 correspondence. Between two sets. Let me state the definition then. So suppose f from x to y is 1-to-1 and onto. It's like one word. Because one of them would not do the trick. Then a function g from y to x going in the opposite direction is called the inverse of f, capital F, g of y is equal to x whenever y is equal to f of x. So from x to y, that's what g does. It is the same as going from, no, vice versa, from x to y under f, and from y to x, under g, like this. Okay, so exactly what we see on this picture, going back and forth. So this one, if we stick with the arrows as we see them, these are f's, but then you can reverse them painlessly like this, and this new function is g. So, well, let's call it black. Black one is the black one is f, the original one, and then we reverse the arrows according to our plan, like this. So in other words, if we make those single arrows double arrows going both ways, it works out just fine. So these are g's. Okay, so the notation is f power, or not exponent, superscript for the inverse. Of f. Okay, so superscript -1, which is certainly is ambiguous in the sense that you are used to this thinking as a power. 2 negative first power is what? 2 negative first power? What? What?
Would be 1.
No.
-2.
No.
1 over f to the first power.
1 over 1 over 2. So negative powers gives you the power of the reciprocal. Okay. So, well, I brought this to mention that this isn't it. So sorry about that if it confuses you, but this is not it, because it stands for literally for the inverse of the inverse of the function. So then that is when we well, we assume that there is only one. Okay, so we assume that it can be easily proven, but let's just assume that there is only one. We usually don't assume anything like that because it is a certain concept is defined for a certain property. Then how do you know that there is only one satisfying the property? But most of the time there is only one. You just have to demonstrate that. You also know that it is possible that such a thing doesn't exist. Say same problem, but fortunately, since we assumed from the beginning that the function is one-to-one onto, then yes, such a thing does exist. There is such a function defined in this manner, and this is its notation. F superscript -1. It is just spoken as F inverse. Okay. So let's look at transformations now. We just spoke of that recently. So inverses of transformations. Here the arrows are not as important. It is better to think of transformation as such. So you take the real line and you do something to it, and then you see if you can undo that effect. So a shift, for example. Shift, we take my x-axis and then I shift it. A shift. Shift 3 units right. That's my F. Okay, F inverse, shift, 3 units left. Okay, so you see how it works out. The inverse will undo the effect of the original function. Undoes F. That's what inverse does. Well, maybe then you can tell me what this means mathematically. Once again, in light of our discussion the last month or so, what does it mean that there are two functions and one undoes the effect of the other? What do I do with these two functions, f and f inverse? Well, I shift once, and then I shift consecutive, carry out another operation. I shift to the left. First operation, transformation, shift to the right. Second, shift to the left. I execute them consecutively, and we call this what? Two operations, functions, transformations executed consecutively, we call this what? What? No, that's in the end, yes. But just in general, what's the term that we have been using for executing functions in a consecutive manner? The word is decomposition. So that is the way to understand the function. Its inverse is that when you compose them together, the effect is nil, or rather the original. So like this, f inverse, what I just described here, composed with f is equal to x. So when we apply this composition of the function its inverse to any number, the output will be the same number. Okay, I have another illustration for that. Here it is. Okay, from boys to balls, and then we carry out another step. So this is my f, and this is my f inverse. So as you can see, if I continue on in that fashion, I will end up with the same. Tom goes to Tom, Ben goes to Ben through this, right? So this one kind of if we are forget about the intermediate stop, then what we end up with is a special function that is has no effect on, it doesn't change anything. Okay, so this is, if you think in terms of arrows, that's what you see. The arrows pretty much they kind of circle like this. Right? If you want to think in terms of transformation, it is even more obvious. It is literally shift 3 units to the right and then to the left. What's the effect of this combination of these steps? Nothing. You will end up where you started. Right? The slightly tricky thing, but really, if you can see it right here, if we reverse the order, and you have f inverse f of y, it's still equal to y. Doesn't matter in which order you go. First f, then f inverse. Gives you the same output as the input. Or you start with the inverse and then you go with the function itself. You say same story applies. Input, or the output is equal to the input. Okay. So if you look at this picture, from x to y to x, and the result is a function from x to x, and it doesn't do anything. And then you can take the other one here. Okay, let's go. Okay, or you go from y to x to y. Once again, soccer ball at the bottom ends up at soccer ball at the bottom. Okay, so this is y, this is x, this is y, this is f. This is f inverse. Okay? So like I said, if you eliminate this, then what's the effect of this composition? There is no effect. Everything remains the same. That is kind of a trivial transformation when there is nothing is happening. Okay, so that's what we mean when we say the inverse undoes the effect of f. It brings everything back where it was. Think about when it is cannot work out. What if f is a fold? I take my x-axis and I fold it in half. Can I undo the effect of this? Can you unfold it? No, the answer is no. And I guess if you want to explain it in some practical terms, it's less more than just a fold. It's like every point loses its identity and it's merged with that point that they brought together. They become one, and so you cannot separate them anymore because it's the same value. So this is with the same point. So you cannot go backwards. And why not? Because the function is not one-to-one. Two points brought together, they cannot be separated after further compositions. If this has happened, see what happens. If you want to illustrate it with arrows, then two elements or numbers brought together to one, whatever happens afterwards, say G, they will stay together. And so you cannot break them apart anymore. Okay? So shift, the inverse of a shift is the shift of the same number. You can express it algebraically very easily. Say f of x is equal to x plus 3. F inverse of y is equal to y minus 3. Well, yeah, you can say that. So you can. How do I know? I just substitute. So y is equal to x plus 3. That's my f. And then if I also write the inverse, f inverse is x is equal to y minus 3. So how do I compute this composition? I substitute. So I substitute y into y. In the second expression, I end up with x equal to x plus 3 minus 3, which is x. So indeed, where the starting point is the same as the ending point, as planned. You can do it the same way, and you take instead substitute x into x like this. Then what do you have? You have y equal y minus 3 plus 3, and the answer is y. And so once again, there is no effect. So geometry, or that's kind of a physical transformation of an object, also matched up with this algebra, simple algebra for the time being. The second example of fold cannot be undone, but there are more examples of, let's go down that list that we did last time. It is when we did transformations of parabolas: shift, flip, and stretch. So number 2 is the flip. What's the inverse of a flip? What? Flip back, fair enough. What's the difference between flip and flip back?
The second action is to turn it back to what it was originally.
Right. But if you have a piece of paper and you describing if you are to describe what you're going to do, what you need to be done to two people, you will tell them one will be executing F and the other one will be executing F inverse. You'll tell them the same instructions. Flip the piece of paper. Then the first person flips the piece of paper. Then the second person comes in, also flips the piece of paper with the same instructions, and the result will be no effect. Again, so we reverse. So the flip is the inverse of itself. Okay, so ultimately it is multiplication by -1. So dividing by -1 or multiplying by -1 is the same thing. So it just happens to be then F is equal to F inverse. It happens sometimes under some special circumstances. The mirror image of the mirror image is what? No, it's the original image. If you put a mirror against the mirror and look at the second, or either one, look at the mirror, reflection of the mirror in the second mirror, you're going to see yourself or without any not distortion, but rather without the flip. Okay. So for example, if you know that if you put a writing against a mirror, you can't read it because it's a mirror image. But if you have another mirror and you look through that mirror, to that mirror, then it will be back to normal. Okay. Okay, number 3 is the stretch. Say stretch by 3. What's the inverse? Right. So algebraically, multiply by 3, divide by 3. Right, so the algebra, it fully applies to everything that you have learned in middle school or earlier. In fact, the inverse of addition is subtraction. The inverse of multiplication is division. Right? So one undoes the effect of the other. So they're just a more advanced view on something that you've seen a lot before. Okay, so one more example of a different kind, and that's what if the function is given by table, or a list of values, rather. X is here, Y is there, this is my F, and I have, say, 0, 1, 2, 3, 4, 5, 0, 1, 1, 1, 2, 3. Okay, so we're going every time. These are the arrows. They imply that usually you don't plot them because it's a table already, but what's behind the table is a bunch of arrows, like these. Okay, so you can add them if you want to. The problem with this is that you will not notice where you have a problem of the kind that we have already we've been talking about, and that is, you see the problem in the middle? If we are now interested in finding the inverse, and once again, the inverse will be given by a table, and it will have table of y's and x's. So hypothetically, you just flip the two columns, and you should have the answer. The problem, what do you see the problem? Well, you discovered right away. You see the problem here? So I have interchanged the two columns. You see what has happened? Well, just draw arrows again. What's the problem? Right there? The problem? The problem we started with today? It's once again not a one-to-one. The original function was not one-to-one, and we run into a problem right here. 3 different outputs of the same input. It is especially noticeable whenever you put them, if it's not visible from the beginning, once you put them in order, maybe using a spreadsheet, you just put it what is it, the ordering button there, order all rows relative to the particular columns. So this one happens to be already arranged, so it will 0, 1, 1, 1, 2, 3, and you have 2 different outputs for the same input. And that is a problem. It is a problem. And where does it come from? It comes from the fact that F is not one-to-one. Okay, so that is helpful. Otherwise, if you ahead of time you have verified that the function is one-to-one and onto, then there should be no trouble. So let me give you an example. But the idea is the same. Interchange the columns, the 2 columns, and then probably also reorder the first one. So usually you have your input list is in order of growth. Okay, so when the y becomes the input, then you want to do the same thing with it. So let me do that once. So this is my F. 0, 1, 2, 3, 4, 5. Well, actually, it's not that easy to think of when we have so few values. Say 1, 2, 3, 4, 5, 6. Okay? Interchange the two columns, y and x. So I'm getting then 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. As you can see, there are no conflicts because they are only one appearance of each x in the first column. So then there can be no conflict. The issue with being onto is not always a big problem because you can always cut the domain of the new function so that it would fit. Okay. So we'll talk more about that, but if you have a list of values representing a function, the main idea is just interchange the columns because it is the same thing. So if you have a function, you're not really building a new function, the inverse, you just take the old function and just look at it in a slightly different way. So inputs become outputs and vice versa. Okay, so some algebra now. So functions when given by formulas. How do we find the inverses? And the plan is very simple. So algebra meaning we're talking about numerical functions. We have y is equal to, say, f of x. To find the inverse, solve for x. Okay, that's the whole story. Because there is no formula, so that's the general rule, is if you have you have your function given by a formula, then to find the formula for the inverse, you solve for x. Because the relation remains the same, as I just said a few times. The relation between x and y remains the same, the rows, the plane have flipped. So if in this formula, original x is the input, y output, all we have to do is just to reverse the roles, and we should be then expressing x in terms of y. So that's the end result that we want to have. Examples are simple, some early on, and so that's not a big deal. So for example, y is equal to f of x is, say, 3x minus 7. Okay, I take my formula y relation. Relation is y is equal to 3x minus 7. Solve for x. So you have y plus 7 is equal to 3x, and x is equal to y plus 7 over 3. So the answer becomes f inverse of y is equal to y plus 7 over 3. Okay? Frequently, you won't know ahead of time whether the function is one-to-one onto, but as you're solving this equation, you will find out. You will find out. Here's an example of how ahead of time you don't know. You say y is equal to x squared, f of x is equal to x squared, and maybe you ask yourself, what's the inverse? And you follow the same plan. The relation is y is equal to x squared. Solve for x. What do you get? X equal to what?
Square root of y.
Almost. Remember what it means to solve an equation. You need to find all x's that satisfy this equation. You missed one. Plus or minus, right? So either you take, assuming that if y is positive to begin with, so that's the second issue. But even if you limit yourself to only positive values, then there will be two possible values of x, and that what you have discovered is that this is not a function, and the conclusion is, if you want to go back to the original, so f of x equal to x squared is what? Is not onto. Is not one-to-one. So that was the nature of the problem. We ended up having two inputs producing the same output. So you take 1 and -1, they give you the the same result. If you did not know that ahead of time, you will discover it when you're looking for the inverse. So in general, how about just solve once and for all the problem of inverses of linear functions? So y is equal to mx plus b, m not 0, okay? Why m is not 0? Because when m is 0, the function is constant. And what's so bad about constant function? It's not one-to-one and onto, or neither one of them. So no inverse. No inverse, and so that's why we exclude them. So solve for x, and you have x equal to y minus b over m. Y minus b over m. So that's once and for all solving the problem of the inverse of a linear function, a linear polynomial. Okay, and then it's probably a good idea to just to take a closer look and compare the, how about we compare the slopes? So f has slope m. What about the f inverse? So once again, this is f inverse. What's the slope of f inverse? Not inverse, but the reciprocal. Yes. So indeed it is 1 over my minus b over m, and indeed if you just look at the coefficient of y, it is the slope. And so that is a very specific relation between two graphs. So for example, if I go with the graph that is y equal to 2x, then the other graph will be like this, slope 1/2. So the steeper the graph of the original function is, the shallower will be, the flatter will be the other one, and vice versa. Okay, so that's how you can solve the problem of slopes of linear functions once and for all. They are all one-to-one onto. Another word is invertible. One-to-one and onto, invertible, meaning that it has the inverse, right? So all linear functions are invertible. Okay, so once again, let me put the table. The inverse is common pairs. So pairs of inverses. We already have seen a few. So addition, or they're adding, let's say, adding k, subtracting k. These are one main pair, or one main pair. The other one is multiplying by k versus dividing by k. So when you describe something by words, it is you don't have to worry about the variables, and you can see clearly how executing them consecutively you will see them canceling each other. So multiply k by k, then divide by k, or vice versa. Will give you the effect of not no effect. Or you first add and then subtract the same number. You once again, that will be undoing the effect of the first. Okay, so the other one we already just seen, and that's a squaring. Squaring the number. What's the inverse? No, there is no one word for it, but so if you square, what's the inverse? Take a square root, right? This one is tricky, then these are easy. This one is tricky because a square is not one-to-one onto. Okay, so you have to be careful with this, and so you have to just stop and work this out, and once and for all, so that you know what it means, what we mean by the square root at the same time as the inverse of the square. And if you look at, just looking at the graphs will tell you what the problem is. The problem is that y equal x squared, it is not onto. If we choose the codomain to be the real numbers, that's not onto, but even bigger problem that is that it is not one-to-one. So what do? We replace the square function with another square function, but with a smaller domain. Okay, so this is still questionable. So what do we do instead? We choose square for x larger than or equal to 0. So I'm limiting my domain to this. As well, I'm limiting the codomain. So domain, and y larger than or equal to 0, the codomain. So which is this. Okay. So that, which means that I get rid of everything except for the first quadrant. So this is all gone. This is all gone. The graph of not only the graph of the function is gone, but the domain codomain are gone. So the whole graph and the whole relation that we're talking about is between the non-negative x's and non-negative y's. So I marked the x. This is my x, the domain, and this is my y over here, the codomain. If that is the case, look at it. So what we're left with is a very simple thing, like this, and this is one-to-one onto. Okay, it's invertible. You can easily verify that the horizontal line test is passed, as well as it will cover every value of y that is available. And then finding the inverse is really no trouble anymore, because all you have to do is just reverse, literally reverse those arrows. Let me do it carefully here. Okay, so if this is my f, going from the x-axis to the graph to the y-axis. Okay, x goes to y like this. What's the inverse? I follow the same arrows in the opposite order like this. Oops. Like this. From the graph of from the y-axis to the graph, the same graph to the x-axis. Okay, so walking back and forth, it is the same relation. The only difference is we're looking at what we assume in this picture to be the input and which one is the output. Well, so this is a relation in the sense that it includes both. So a relation includes both f and f inverse. If you want to extract one at the expense of the other, then you have to do extra work. This one is y equal f of x. That is where x, the input, y is the output. So if you want to look at the inverse function, then what do you have to do? You just have to flip the x's. So you make sure then the y-axis then, well, let me, x-axis, let's make it in red, so it will become vertical. That's my x-axis. And say this is my y-axis, the green one, it becomes horizontal. But there is nothing else. The relation remains the same. So the once again, we're thinking about the xy plane as if it is a piece of paper with a drawing on it. We just flip it. So the drawing of the graph will remain there and it'll look like this. Y equal, rather x equal f inverse of y. So, so the difference is clear. So you can see how as x is growing on the left, y is growing faster and faster and faster. Okay. The opposite story becomes on the right. It is when y is growing, x is growing slower and slower. Okay. So, but like I said, it's exactly the same picture. Imagine having a piece of paper or a transparent plastic with a drawing on it. Well, let's do that with paint, because that's it's a good exercise. So okay, so I'm drawing the axes first. That's not right. Okay, now I'm drawing the graph. Okay, so actually let me do the way I did it. So the red will be vertical and the green will be, well, red is horizontal and green is vertical. Okay. Okay, now I'm plotting the graph of say y equals x squared. Okay, so like this. I try to draw a parabola here, maybe like this. Okay, looks reasonable. Okay, now I'm going to be flipping. Okay, so let me mark this with x and this with y. Okay, so now let's flip it. Okay, so we have these rotations, and I need to flip it like this, which will take two operations. Can you tell me what they are? How do I make y pointing to the right and x point up? Just tell me what the first one is. Flip vertically. Okay, flip vertically. Okay, and now what? And what? Rotate 90 degrees counterclockwise, right? Okay, exactly. So you can see the match, right? So exactly what we just did by hand, we did it with paint. Okay, so I'll stop here. I'll see if I'll try. What